this. Yeah. Now see here, I will show you the model of cyclohexane. Observe this. I hope you can see it on the board. Let me see that. Yeah. Oh, somebody is waiting. One second. Yeah. See on the board, not very clearly visible, but still you manage. One second. Let me arrange it. It's a bit difficult to hold it in there. Yeah. Now see the cyclohexane. First, let me show it like this. Okay, this is the cyclohexane. Now you can see here. Holding this in the proper perspective is very difficult once through the window. Now see, if you look from the front, if you look at the cyclohexane, actually you can see only 4 bonds. Four carbons, sorry. Actually you can see only 4 carbons. This is one. This is the second. This is the third. And the one which I am holding here is a fourth, this one. You can see only 4 carbons. Right? You can only see 4 carbons if you are looking from the front. Right? You can see only 4 carbons if you are looking from the front. And that is why, and see here, I will mark these carbons here. 1, 2, 3, 4. These 4 carbons only you can see. But since you want to see, since you want to observe the molecule, since you want all the 6 carbons to be seen, what we generally do is, we draw the molecule, we hold the molecule slightly bent. See here, bend it slightly towards the front. Now see, you can see all the 6 carbons. Ideally, it should be like this. You should be able to see only 4 carbons. That's the ideal situation. But if I draw only 4 carbon, nobody will tell you that it is cyclohexane. So what we do is slightly bend it towards the front side. See. Right? Now all the 6 carbons are seen. Here you can see 3 of them. And here you can see 3 of them. Clear? See, this is the cyclohexane molecule. Now let me see. This is the up carbon. See, assume I'm sitting in this chair. See, I'm sitting here in this chair. So this is my head. See, this one is, here is my head. I hope you can see it. And this is where I keep my leg. And these 2 are my knees, 2 knees. Okay. Now these 2 down here, these are my buttocks down here. So now assume you are sitting like that. You are sitting yourself with your head on the top, the 2 buttocks here, and then you are bending your knees here, and you have the legs here. Right? Now you can see here the bond pointing up, this one. This is axial bond. This is axial bond. And this is axial bond. They are three pointing up. And here you have three pointing down here. Oh, one is missing. Let me take one bond. I have to make. Okay, down. One second. Let me take the bond. Yes. Here is one. See here. Which are the down bonds? Pointing perfectly down, axial, axial, and axial. Okay, so these are the axial bonds. Now see here. Now let us look at the equatorial bonds. See this. This is equatorial. Pointing to the side. This is equatorial, but this is pointing up, but to the side. This is pointing up to the side. This is pointing down to the side. This is pointing up to the side. This is pointing down to the side. And this is pointing up to the side. So these are the equatorial bonds. Now you have to tell me what is the relationship here. See here, this bond and this bond. This is axial, this is equatorial. Okay? This bond and this bond. Are they cis or trans? Are they cis or trans? This and this. Are they cis or trans? Write your answers in a paper. Now look at this one. These two. This is evidently they are trans. See here. This one and this one, they are trans. Since these two are trans, these two has to be cis. So you just have to see whether pointing up or pointing down to see whether it is cis or trans. Okay, so now let me draw it on the board. Look here, this and this, they are trans because one is pointing up, other is pointing down. Okay, this one, and this one, they are cis. This pointing up is also pointing up. They are cis. So you should know what is the relationship, whether it is cis or trans. Now let me show you what happens to this. Yeah. Now see what happens. This is the cyclohexane molecule. Now see what I'm going to do. What I'm going to do is I'm going to bend this molecule slightly to the upper side. I don't know how far you can see this in the. Now see here, I'm going to bend this molecule and down. See. Right? This side up carbon I have brought down. Or I can do one thing here. See here. I bring this side to the upper side. What has happened? The chair form has become a boat form. This is the chair, this is a boat form. What I have done is, I have taken this side and pressed it up. rotated it upside. So this has become boat. But boat form is not stable. You know why? These two hydrogens are very close to each other. The upper hydrogens are very close to each other. So the boat form is not very stable. So what happens is this gets repelled and this bends down again. So what has happened? The whole chair is flipped. See here. See, there's a continuous conversion of this to this, mutually between each other. And this process is known as chair flip. That is conversion of one chair form into the other. Now let me draw that. See here, this is the chair form which we have drawn. We have already drawn. What? This is the one. Now what should I do? Look here. This is. What has actually happened is I have brought this down, pressed it down, and pressed this up. Okay. So it becomes this form. This is called chair flip. Chair flip. And remember, this requires energy, very small amount of energy, something like 2 kilocalories per mole. Which is obtained by Brownian movement itself. Since the molecules are hitting with each other, some amount of energy is released. And that energy is sufficient to convert this form into this form. So in a sample of cyclohexane, this interconversion is occurring 10,000 times per second. 10,000 times it is getting interconverted per second. So continuously this is getting interconverted. One chair form is getting converted to other chair form. And intermediate is somewhat very similar to boat form, but exactly not the boat form. Okay. So that is the chair flip, and this is occurring 10,000 times per second. And during the chair flip, see here, this is H. This is H. I will just say this is H axial, and this is H equatorial. Okay. Now this bond is coming down. So this is, let me mark this as carbon 1. Now where does the carbon 1 come here? This is the carbon 1. Now see, if this is bent, the A will become E here. This A, the axial bond will become equatorial, and this equatorial bond will become axial. Okay, so during the chair flip, axial bond will become equatorial, equatorial bond will become axial. You can, if you want to see it, you can see that. You just observe this bond. See here, this is, observe this bond. Let me do the chair flip. See this. See, it has become equatorial now. This has become axial. Let me rotate it back. See here. Okay, just one second. Oh, oh. Okay. So I was. So this is a chair flip. So I have shown you this is equatorial bond. It's an axial bond. So during the chair flip, axial will become equatorial. Equatorial will become axial. All the bonds, not only this one. If you rotate this one, all these axial bonds will become equatorial. Equatorial bonds will become axial. Right now. So that is about the chair flip. Now stability point of view. Now looking at the stability. Looking at the stability of this. Chair form is stable than boat form. So this is chair. Now this is the boat form. Okay, so one side has gone up. You form the boat. Now this side will come down. And this is sorry, the second chair. Second chair form. Clear? So this is now stability point of view. This is more stable. This is stable. This is less stable. Because of this hydrogen interaction. These two hydrogens are very close to each other. These two hydrogens are very close to each other, and they are very, and they interact with each other. See here, and this is called flat pole interaction. Flat pole interaction. So flat pole hydrogen interaction. Flat pole hydrogen interaction. So that will make it. So these two hydrogen want to become as away from possible, as far as away from possible as possible. See here, H and H, they are very far away. If in the board, see in the chair form, in the board form, you can see these two hydrogens are very close. These two hydrogens. See, these two hydrogens are coming here. Okay, so that is what is meant by chair flip. And now let us look at these substituted cyclohexane. Look at this one. I put a CH3 here. If I put a CH3 over here, let me draw the full structure of the CH3 group. Remove this H and put the full structure. I have got H here, another H here, and a third H here. Okay, and remember the rotation around this single bond is allowed. So this hydrogen will be keep on changing the place. Now you can see here there is a hydrogen, and here also there is a hydrogen. So you have two hydrogens here and here. So these are very close to each other. And this interaction is known as 1,3 diaxial interaction. 1,3 diaxial interaction. Okay, so that is a destabilizing factor. It will destabilize the molecule. So this conformer is destabilized. So axial groups, if you put molecules in the axial group, they will interact with the substituents on the third carbons. This is, if you put it on here, 1, 2, 3, 1, 2, 3. They will have interaction between each other, steric interaction, and that will destabilize the molecule. So what will happen? They will undergo chair flip. And during the chair, I told you during the chair flip, axial will become equatorial, and equatorial will become axial. Now see here, the CH3 will come here now. Right? So there is no interaction. So equatorial substituents are more stable. Equatorial substituents are more stable. Okay. So, and therefore you have to write this equilibrium this way. You have to write this equilibrium in this fashion. See this. What's the meaning? What's the meaning? The meaning is more amount of equatorial form is present at equilibrium. More amount of equatorial form is present at equilibrium. Okay, so the CH3 group, it's a bulky group. CH3 is a bulky group. Bulky groups prefer to be in the equatorial position. Clear? They prefer to be in the equatorial position. So this is the mono-substituted cyclohexane. Mono-substituted cyclohexanes. So what is a brief about it? In mono-substituted cyclohexanes, the substituents prefer to get converted to occupy equatorial position. Occupy equatorial position. Depending on their bulkiness. Depending on the bulkiness of the group. The more bigger it is, more it will prefer to occupy equatorial position. Bulkiness of the group. See, if it is methyl group, you can say 90% is equatorial, 10% is axial. Okay, but if it is a T-butyl group, if it is a T-butyl group like this, see here, 99% will have this form. 99% is this. Hardly any form will be in the axial position. Very less than 1%. It's more than 99%. So it is a bulkiness of the group which decides the stability of the conformation. Is it clear? So that is about the conformation of cyclohexane and their stability. The stability is depending on 1,3 diaxial interaction. See here, this is what is 1,3 diaxial interaction. If you are asked to, okay, you just have to show this. That's all. This is 1,3 diaxial interaction. Interaction between the substituents in the first and the third carbons between each other. So this is these are the brief about the cyclohexane molecule and their conformations. Remember, we have not broken any bond here. We have converted all by simple rotation of the molecule or the group. We have not broken any bond. Therefore, without breaking, if you can convert one form of a compound into another form, without breaking a bond, if you can convert one form of a compound into another form of the same compound, you call this as conformations. These two are two different conformations. Like, see, ethane, it has got two conformations, major conformations, stable conformation. One is a staggered conformation, and the other is eclipse conformation. Staggered and eclipse. Now, what about cyclohexane? You have two chair forms. Two chair forms is boat form. These are two different conformations of cyclohexane. Okay, so that is very briefly about conformations. Now let us look at geometric isomerism. What is geometric isomerism? Geometric isomerism, it occurs with molecules. It is observed in molecules with double bonds or rings. I think we discussed this. No. Okay. Anyway, I'll discuss it. I think we discussed this before. Anyway, molecules with double bond or ring. If the groups are on the same side, opposite side, called as strands. If they are on the same side, you got as cis. Okay. The trans components will not have dipole moment. So dipole moment equal to 0 if it is symmetric. Suppose you have carboxylic acid group here. This is what is called malic acid, fumaric acid. This is fumaric acid. 2 carboxylic acid groups. And here it is malic acid. Malic acid. Malic acid. And here and here, see here. Here the dipole moment is, this bond is polar. It is pointing towards this side. Here it is pointing towards this side. So they mutually cancel with each other, and therefore mu equal to 0. Dipole moment is 0. But here, this is the, now here this is pointing this side, and this here, this bond is pointing, the dipole moment is this side. So the average of this, that is the resultant of this, will be in this direction. So this side is delta positive, this side is delta negative. So that means it has got a positive dipole moment, more than 0. Okay. So this is the property difference between them. And they have different properties. These are more stable. More stable. Thermally resistant. Thermally resistant. It can withstand more heat. Higher melting point. Higher melting point. Lower melting point. And also one of the important things is, see here, this molecule cannot form an anhydride. This molecule cannot form an anhydride easily. But here, look at the way it is forming an anhydride. See, you have the OH here, double bond, C double bond O and H. Okay. See how it is forming an anhydride.